Well, as I observed earlier in this series of lectures, most of neoclassical economics looks persuasive to its devotees, but actually they're like the fairy tales of old, and in fact fractured fairy tales. They never actually work exactly as their proponents would like them to believe. And one of the most prominent of these is the Cobb-Douglas Production Function, which dominates the way that neoclassicals model production today. If you go back 30 or 40 years ago, say 30 years ago when I was doing my PhD, most of my fellow PhD students were building a computable general equilibrium model of their national economies. Now, as much as I'm a critic of CGE models, they have one great advantage over the Cobb-Douglas Production Function, and that is that they have to include inputs from other sectors as necessary inputs to produce output from your sector. And one of the sectors that they include has to be mining, another energy. So in that sense, there was a real world connection to the production functions that were used back in the days when CGE models were the ants pants in neoclassical economics. But ever since the switch to so-called rational expectations and the models developed by Lucas and Sargent, Rapping, etc., the Cobb-Douglas Production Function has become the dominant model. Now, sometimes I'll use what they call the CES, or constant elasticity of substitution model again, which appears to be more flexible. But in fact, when I talk a bit more about a paper done by Rudy Bachman on energy later in these lectures, you'll see just how, well, not unusable, but far too critically sensitive that model is to actually be used. So most of the time, if they do an applied model, it'll have a Cobb-Douglas production function at its heart, and therefore we have to see just how sound this particular heart is. Now, this is the basic equation. They say output, which they might use the symbol Q or Y for, is some variable. I've got it there just as alpha. They normally use A instead, but I'm using alpha here just in this illustration. So alpha is a time-varying argument that reflects the level of technology in their normal way of thinking. So there's your quantity, there's your technology coefficient, which varies over time, multiplied by the number of workers, which is L, and the number and the exponent for each of these, for L and K, reflect the income shares that particular factor of production, so-called, gets in the economy. So L and K are the number of workers and number of machines respectively. Beta is the income share of the workers. Now that should be 0.7 when it's done empirically, and the K is the 1 minus beta is the share going to machines, which is normally about 30%. And what the neoclassicals love about this model, by the way, later I think I'll swap around what I put the beta and 1 minus beta to, the same basic argument holds. Neoclassicals love this model because it encapsulates all the false beliefs they have about production and the distribution of income. So the first one is you can show that this equation necessarily gives you diminishing marginal productivity, which means rising marginal cost, which, as I showed in the first lecture, does not exist in the real world, but it's essential to neoclassical theory. The returns to the factors of production, the wage rate and the profit rate respectively, reflect the marginal product, and that again is part of the religion, that your return reflects your contribution to production. And then let's show the diminishing marginal productivity side of things. So you have the argument that each additional worker will add a positive amount to the level of output, but less than the previous worker did. So if we take a look at the quantity equation there and differentiate it with respect to labour, then that gives us the rate of change of output with respect to labour, which they call the marginal product of labour. So you differentiate with respect to labour, so you look at dq dl, and that's the simple differentiation. You get L to the beta minus 1 as the outcome on the L side, and the constant beta comes out the front. So you get alpha times beta times L to the beta minus 1 times K to the 1 minus beta. Now, if you then rearrange things, you can take beta out the front and divide the second expression by L, and hey presto, that the expression on the numerator there is, pardon me, press the wrong key in my mouse here, that expression is Q. So you do the substitution and you get the marginal product of labour is beta, which is the income share, when it's fitted empirically, multiplied by Q over L, and because this ratio is going to fall as you add more and more labour, so you have this is the diminishing marginal productivity component, therefore the marginal product of labour will fall. Now then, if you invert the expression and multiply by the wage rate, you get the marginal cost, and the wage here is assumed constant because of the assumption that you're paying, the individual producer is paying a constant wage to get workers of constant quality to extend their workforce. So W is a constant from the point of view of the firm being considered here. You still get the L over Q ratio, so L is going to rise faster than Q, and therefore you get rising marginal cost. So that's the one reason they love this model. It fits in so nicely to their way of thinking. And so you get rising marginal cost, which is what they need for their theories to work. Now, they'll often claim, well, it might be a theoretical thing, it might be we made it up and then fitted it to data, but it did fit the data. It fits national data really, really well. And researcher Fisher made this point rather well in 1971, saying that they appear to fit the data in a way that is not easy to explain. The marginal product of labour appears to give a reasonably good explanation of wages, and that justifies the whole meritocratic attitude that neoclassical economists have towards the real world. I hope you can still see my face here. I'm just getting saturated by sunshine coming through Margate as the storm that just went through passes, but if I'm suddenly getting lighter and the screens are getting darker, I'll just have to live with that. Now, Solo once remarked to Fisher that had Douglas found labour share to be 25%, and capital 75 instead of the other way around, we would not now be discussing aggregate production functions. So the fact that this correspondence between the model and the way the data and the way the model explains the data, that coincidence is a major reason why this particular production function became popular. And Fisher finishes, this is 1971 notice, saying that the estimated aggregate production function to explain wages fairly well is a statistical artifact, then it certainly is not an obvious one. And that's true. I took a brilliant paper by Anwar Shaikh, and Anwar, I've always said this, my hat's off to you for a brilliant piece of work here. He showed in a beautiful paper called The Laws of Algebra and Laws of Production, the Humbug Production Function, back in 1974, that the Cobb-Douglas Production Function is basically derived from the output equals wages plus profits identity under the condition of slowly changing income shares. And he actually ended up, as part of the reason the title is so interesting and the content of the paper is so interesting, he simply wrote the word humbug on a graph. You can see that that's done in the old days of using a pen and graph paper to mark out the graph. He wrote the word humbug, and then the dots you can see there became data points. And he showed you can fit humbug with the Cobb-Douglas production function. I think it was a beautiful piece of rhetoric as well as logic. Well, let's go through it and see how he worked it out. So what he's arguing, and he proves very simply, is that the Cobb-Douglas production function is simply a transformation of the national income identity that output equals wages plus profits if income shares are relatively stable over time, which they are, even though they've been moving since then in the direction of capital and against labour. So if you start by saying income is equal to wages plus profits in real terms, there's your starting point. And you now assume an average wage and an average rate of profit, which is your first step of simplifying things to mean you don't get a perfect fit to the data. But that's how to generalise the model. So you're now saying quantity is the wage rate times the number of workers plus the rate of profit times the number of machines. And let's look at the rate of change of that. So you differentiate those with respect to time. So the rate of change of Q with respect to time is going to be the rate of change of W times L plus the rate of times of R times K. And you've got a simple product rule there, so you expand out. D dt of W times L is W times dL dt plus L times dW dt. And the same thing for the rate of profit. And now let's make into percentage rates of time, which means I divide all the way through by 1 over Q. So I don't transform the whole equation. So 1 over Q dQ dt is the percentage rate of change of output. And now leaving out the the middle line there, that's going to be W over Q, so you've got this and divided by Q, L over Q, again, R over Q, and K over Q. So you now have a slightly more general expression. It might be hard to work out where you're going through at this point, but let's now see. Well, now just to simplify the whole thing, I'm multiplying each of the expressions by the missing term. So this is dl dt. I had W over Q times dl dt. Now I'm multiplying it L over L. I'm multiplying the L term by W over W, the R term by K over K, and the K term by R over R. Now again, I haven't changed anything. I've just introduced another term to enable us to analyse what's going on. And let's now shuffle things around. So I'm now going to bring the W over the L over here, which means I've got, rather than W over Q times L over L, I've got W times L over Q multiplied by 1 over L dl dt, and this is now the rate of change of the labour force. Ditto here, rate of change of wages, rate of change of capital stock, rate of change of the rate of profit. And then all throughout here, I've got that as the workers' share of GDP, which we're going to use the term omega for. This is the capitalist share of GDP, which I think I used the term pi r for, let's see. So all the terms on the right-hand side now include the distribution of income, the workers' share and the capitalist share of income. So there's omega for the wages share, and yeah, I use pi, which is equal to 1 minus omega, times the capitalist share. So rearrange that, just to substitute omega and 1 minus omega for W over times L over Q and R times K over Q respectively. And now we have the argument that income shares move fairly gradually, so we can actually apply a rule of differentiation and integration here. So 1 over f of t df dt, the function, is very equal to the differential of the log of the function. And if I do that, if I have 1 over f df dt, integral of 1 over f times df dt, then that is equal to the integral of the differential of the log. The integral and the differential cancel each other out. That's what's going on here. And you get this whole term here is equal to the log of the function. Okay? So, and therefore, the integral of 1 over q dq dt is equal to the log of q. So we apply that to both sides of the percentage rate of change expression. And now what I've got is the log of q is equal to omega times the log of L plus omega times the log of W plus 1 minus omega times the log of K plus 1 minus omega times the log of R. Okay, now we then take the simple mathematical rule that a constant times the log is same as the log of the function raised to the power of that constant. And now to reverse the logarithm, we take the exponential, and that's going to give us Q is equal to e raised to the power of all those elements. You expand that out. I'm doing it step by step so you can follow this more carefully, and I'll paste this set of lectures on my Patreon page at some point so that people can download them and look through them slowly. So now what I've got is L raised to the omega times W raised to the omega, and K to the 1 minus omega times R to the 1 minus omega. Shuffle that around, bring the wages raised to the power of omega and the rate of profit raised to the power of 1 minus omega out the front, and I've almost got the Cobb-Douglas Production Function. If I define alpha being equal to the wage rate raised to the wages share of output and times the rate of profit means 1 minus R. Now, that's all simply working from an accounting identity and using the short-term accurate approximation that income shares don't change rapidly, therefore I can take them outside the integration operation as a constant. Now, if you then try to test this so-called model of production against the empirical data, of course you're going to get good correlation because it's simply a transformation of the empirical data. It's regressing an identity against itself. And the only reason you don't get a perfect correlation every time is because the income shares in fact do change somewhat slowly. So you won't necessarily get a perfect correlation, but you get a very high one. In no way does it empirically validate the theory. This is the problem. That's how it's taken. Again, this is because the neoclassical economists don't look deeply enough under the hood of their beloved models. So it's just empirically validating that yes, income is equal to wages plus profits. That's all that's really going on. It's not really a production function. And the solar residual may just be empirical nonsense rather than a measure of technological change. That's that bit up there. Now, that may have been too fast, so I'm going to go again through it more slowly. We're going to define output as being wages plus profits and assume a uniform wage and a uniform rate of return. So you're starting from this expression, y equals w times L plus r times k. Differentiate with respect to time, so I'm going to have dy dt and then ddt of w times L, etc. Divide by y and multiply by terms in L over L, W over W, K over K, and R over R, respectively. So that's one step to get to that particular point. I'll let you have a look at a flick through that line. Rearrange it into income shares and rates of change. So I've now got W times L, and times 1 over L dt, etc. Substitute r to the k over y equals alpha, which is the usual term neoclassicals use for the exponent, and w over L equal to 1 minus alpha, and you then get the differential of the log, as shown earlier, is equal to all those expressions. Integrate them. To integrate now, and the integral of the differential just gets out the log term out of the whole expression. Take exponentials, and there's your Cobb-Douglas production function. So we've gone from this to that by a series of quite straightforward logical mathematical steps, just with the only condition that the wages share and the rate of profit share don't change all that rapidly, so we can treat them as constants when we do the integration. Boom. A is equal to W raised to the 1 minus alpha times R to the alpha. It's the Cobb-Douglas production function. Yes, it's going to fit the empirical data. But it's meaningless because, and this is, I think I'm quoting Shaikh here. Oh, I might be actually quoting Philippe here. Philippe and Macombi have carried on Shaikh's work since then. Since the data and output and inputs is linked through the accounting identity, the aggregate production function will approximate this income accounting identity. It's an algebraic transformation of the identity under the appropriate assumptions about the data, yields a form that resembles a production function. So the correct form of the identity, when it's fitted to the data, is going to fit very well the argument that you've got constant returns to scale and that factor markets are competitive. All it proves is that neoclassicals don't look carefully at their own mathematics. And there's one more problem which I haven't gone into yet. It's my own contribution here, because what you have there as an output function has no external inputs into it at all. There's no matter from the outside world. There's no energy from the biosphere into the whole system. I've included that in my own work subsequently, and that puts yet another hole in the theory of neoclassical theory of production. Now, why do they stick with a false model? It's, again, this is the reason they stick with loanable funds in analysed banking. It maintains their belief that capitalism is a meritocracy. And it is, pardon me, I've got to do that. Okay, I'll snooze that for a few minutes, maybe more than 5. Sorry if I've got a double reminder for the next seminar I'm attending here. So the way this comes about is that when you first learn neoclassical economics, and I first learned it at high school at the age of 16, you learn what looks like a mathematical analysis of capitalism, but it ends up being something that says that capitalism is an ideal social system. It's a meritocracy. You get paid your return, your wage, your income reflects your contribution to production. So you're getting what you deserve. It also maximises your utility, etc., etc. All these things end up making you see capitalism is an ideal social system, so long as it conforms to what your textbook says is the ideal. So you want to have competitive markets, you don't want to have trade unions, etc., etc. And that makes neoclassicals zealots about capitalism, which they see as being their model. Their model is completely wrong as a description of reality, but they defend the model against any attack, including this attack by Shaikh, which was taken on by Solo, without changing the basic logic here. So what they see is the marginal product of labour, they see as the real wage. That's the exponent of L in the Cobb-Douglas Production Function, and it's roughly, it's the same as the labour share of national income, roughly 70%, or 0.7. The marginal product of capital is supposed to be the exponent of capital in the Cobb-Douglas Production Function. That's roughly 0.3. And when you get it, you get this tautological outcome that makes it look like it's quite okay. But here I've got to take my hat off to a neoclassical I normally criticise, and that's Gregory Mankiw. Because he did a beautiful piece of work back in 1995 showing that while the Cobb-Douglas Production Function, for reasons I've just outlined, fits the empirical data for a single nation really, really well, when you do cross-country comparisons, it's a total disaster. So here's Gregory Mankiw's paper, 1995, and his conclusion was the capital share should be set at about 0.8, so not 0.3 as you get, as I've shown above in this slide, when you do the empirical fit to an individual country. If you want to make it fit the international data, you've got to make it 0.8. Now, if you do that, you no longer have the theory justifying the attitude about the distribution of income. And so Mankiw's paper, which I think was a brilliant paper, has not been incorporated at all by neoclassicals in their model. They still use exponents of 0.3 for capital, whereas Mankiw said it should be about 0.8. And when I go into talking about energy, you'll see why that's so important. So here's some excerpts from Mankiw's paper. I won't attempt to summarise it. It'd take a very long time to explain his mathematics, and not longer than I have in this particular lecture series. But he says there are large differences in income in the real world. If you look at savings rates, you find a multiple of 4 in the differences between saving rates, and population growths that vary about by 2%. So what you get is that the model can therefore explain differences in income between countries of slightly more than 2. So in that case, Bangladesh should have about half the income per person of America. In fact, you get disparities of more about the order of 10. So it's using the standard coefficients of 0.3 for capital and 0.7 for labour, you get a result that says the income difference per capita between America and Bangladesh should be a factor of 2, when it's much more than a factor of 10. Then your model also predicts convergence of growth rates. There is empirical data on growth rates converging, but it predicts it happening about twice as fast as actually happens. Now this is the real clincher. Because you have about 1/10 of the income in poor countries per capita versus rich, according to the model, when you use the standard coefficients, the return to capital should be 100 times as large in third world countries as it is in developing countries. And that means you should have a profit rate in third world countries of 1,000% per year. And Mankiw simply says you don't need data to show that's nonsense. There's something wrong with it. So when he looked at the equations, and he did quite a bit of work to rework the Cobb-Douglas Production Function into various other forms, he found that the rate of growth of income, I've forgotten what he used lambda for, I need to look at it again, but these 3 terms all had an essential role for the role of alpha and 1 minus alpha. Notice you have alpha over 1 minus alpha here, 1 minus alpha here, and 1 minus alpha over divided by alpha. Here, the inverse of what you've got up there. You said, now, what if, and this is, again, I have to, I'll give myself a longer snooze here. Okay. What if the capital share, alpha, in this expression, were 2/3 rather than 1/3? You said, well, if a country had 4 times the saving rate, it'd have 16 times the income per person. And that's, therefore, roughly the magnitude of difference we see. You'll get a rate of convergence which corresponds to what empirical research says it is, and the predicted differential of returns falls from a multiple of 100, which is 10 squared, to a model of 3.16, which is 10 to the half. And it said if the capital share is larger than 2/3, the predicted differential in returns to the rate of the capital between developing countries and developed countries is smaller still. Now, how did neoclassicals react to this brilliant piece of empirical research? They didn't react at all. They still assume alpha is equal to 0.3. And this is one reason I say neoclassical economics is literature. It's not science. Because if a scientific discovery was made that a value of some fundamental parameter was substantially different to what theoreticians had originally thought, then over time, very rapidly in most sciences, that numerical revision would be respected, and anybody who set the value to the old value to be told, look, you're out of date, you're being unscientific. But if you check the latest, very latest neoclassical models, particularly those in the climate change world, they're still setting the exponent for capital equal to 0.3. So this is one of the examples I'll give of this, and I'm going to finish this lecture, go on to the next workshop, and then I'll come back to this topic when I start talking about the role of energy in production. There's a paper, a very, very topical paper right now from a working paper of 2022, where Friede and a range of other German economists argue against the production function that Post Keynesians use, and that I've used in the model that I built with Minsky just a moment ago. They dismissed that on the basis that you can't justify, they say, the argument that there's a one-for-one decline in output with each decline in energy. And so using the standard Cobb-Douglas Production Function and treating energy as the third factor of production, Brackman and friends concluded that because the coefficient for energy would be 0.04, a 10% fall in energy would cause a 0.4% fall in GDP. Now, with the Leontief Production Function, which is the one that post-Keynesians use, a 10% fall in energy means a 10% fall in GDP. And I'll continue on this particular issue in the next lecture after the next workshop. And the next lecture will be on the neoclassical blind spot on energy, which I think is probably the most consequential blind spot in the history of economics, because that's what's led us into the ecological crises we're now starting to experience.